Good morning, and thank you for the opportunity to share with you our plan to enhance MCNP to include the modeling of electron-screened ions. My colleague Larry Forsley and I have been researching nuclear fusion for the past 6 years as part of a team at the NASA Glenn Research Center. We are happy to be here at this symposium. First, as a little background, lattice confinement fusion is a method where a metal lattice is loaded with deuterium. A triggering mechanism is applied, such as Bremsstrahlung radiation, and the DD fusion events result from an electron cloud in the metal lattice that screens the deuterons' positive charges from one another. This method has been researched and published in the Physical Review C journal. During this presentation, I will provide an introduction of the research behind our proposed MCNP enhancements and a short description of MCNP's current fusion modeling capabilities. Larry will then talk about the MCNP modeling we completed during the LCF research project, the limitations we encountered during our modeling efforts, and the enhancements we propose to include within MCNP. I will then provide a summary to wrap up our talk. The research behind the impetus for the proposed MCNP enhancements comes from many years of experimental and theoretical work. At both Glenn's Research Center and the Department of Energy's Lawrence Berkeley Laboratories, a novel means of driving nuclear fusion reactions in these deuterated metal lattices was discovered during either Bremsstrahlung at GRC or plasma discharge-based experiments at LBNL. Both teams published papers in scientific journals. A companion paper was also published by our team at GRC that describes the electron screening theory behind the nuclear events observed during the Bremsstrahlung-based experiments, whereby the metal lattices provide the electron screening necessary to reduce the Coulomb barrier and facilitate the DD reactions. Other researchers, such as Salpeter in 1954 and Sigursky in 2006, have proposed electron screening as a way to increase the DD fusion rate, and their research helped guide us along our way. Early on in our research, we also realized that MCNP could be an excellent guide in modeling our electron-screened deuterated lattice nuclear fusion findings. We started modeling gamma-ray irradiated metals, nuclear activation, fission, and shielding, and then, after our most recent experimental campaign, we used MCNP to model the detector responses that enabled us to determine that we detected fusion neutrons during our Bremsstrahlung experiments. However, we, nor LBNL, were able to model the true details of LCF nuclear reactions with MCNP, or for that matter, GEONT-4. So Larry and I did a search of the current MCNP fusion modeling capabilities and found out how current MCNP users are working with the modeling environment. In this first paper, Zeeb's team provided a review of heavy charged particle transport within MCNP, and from their paper, we realized that while electron screening could be modeled in MCNP, only charged particles of energies higher than 100 keV are supported. The charged particles involved in our research are at much lower energies. Another group modeled 40 MeV accelerated deuterons on lithium-6 and 7 as a neutron source. For the highly recognized tokamak fusion, only neutron propagation and interaction has been modeled, as described in this trio of papers. The laser fusion community has modeled a neutron source only for a hybrid fusion fission reactor. And finally, from the brief literature search that we performed, we found yet another researcher using MCNP to model neutron transport and activation, but not the DD or DT fusion reactions. Next, Larry will provide more details about the MCNP modeling we completed, the limitations we encountered, and the proposed enhancements we intend to develop.
Thank you, Teresa. I'm Larry Forsley. I'm going to talk about the MCNP-related modeling we've done under the LCF. First, we modeled 1 eV to 15 MeV photons from the Bremsstrahlung photoneutron trigger we used, and also 10 eV to 15 MeV electrons. We also modeled thermal, epithermal, and fast neutrons using the VisEd visual editor with MCNP6. We've also modeled actinide fission, and we've seen here in this lower figure a synthetic high purity germanium detector output. We also modeled the neutron spectrometer response functions for the different scintillators and the moderated plane neutron capture device we used. However, we can only track ions over 100 keV, and we can only model ions that have over 1 MeV from the fusion products. Now look at the calculations we did after we finished the modeling. First, we did pulse shape discrimination so that we could separate neutrons from the gammas in the window. We had a window set at 8 sigma to try to throw out as many gammas or all the gammas. Having done this, we then unfolded the neutron spectrum, subtracting out our fueled or non-deuterated erbium from the deuterated erbium. We have a 2.5 MeV roughly DD fusion neutrons, and we have 2 peaks of boosted fusion neutrons. Whereupon we found the limits that we've got on doing nuclear reaction modeling with MCNP, GANT4, or with SRM-TRIB. In particular, in MCNP, there's no model for DD, DT, or D-helium-3 fusion whose reaction cross-section peaks are below 1 MeV. Nor is there a model for electron-screened ions less than 10 keV. And the SRM-TRIB modeling allows us to model ion scattering within the lattice, but it doesn't do the nuclear reactions. Nor is there a model for electron-screened deuteron stripping reactions where the proton or the neutron is stripped away from the deuteron onto the host metal lattice. So these are some of the proposed enhancements. First, we'd like to incorporate the Frascati fusion neutron generator subroutines. These handle 10 to 50 keV deuterons, and this was developed for the International Thermonuclear Experimental Reactor. Then we can test these with our own data from 64 keV average deuterons, 32 keV in the center of mass. And as you can see on the chart to the right, as these deuterons recoil off the fast neutrons and enter into the lattice, they slow down. And they'll reach a point where the electron screening begins to become a predominant mechanism. Hence, we can add from our theory paper an enhancement factor, F sub E, for electron screening at less than the 10 keV deuteron kinetic energy. We can then test that with the Lawrence Berkeley National Lab's plasma glow discharge means of driving lattice confinement fusion, where they're working between a 1.25 and 6 keV center of mass deuteron kinetic energy. Finally, we can add density functional theory and dynamic density functional theory to allow us to calculate out the electron screening effects below 1 keV and essentially modify the gamma and the astrophysical factors.
In summary, today we have outlined a list of enhancements that we would like to provide and include in MCNP. We propose to add ion scattering from 10 keV to over 64 keV and add electron screening of ions from below 1 keV to 10 keV. We believe that these enhancements would benefit both NASA and the Department of Energy's research with terrestrial and space-based fusion reactors, gain a better understanding of the astrophysics behind warm dense matter and stellar nucleosynthesis, and help us differentiate between boosted fusion and stripped or ejected neutrons observed within our experiments. Furthermore, we are very interested in partnering with Los Alamos National Lab's MCNP developers to fully incorporate these enhancements into future releases of MCNP, which lines up with the current NASA DOE Memorandum of Understanding on Space Nuclear Power. With that, I'd like to thank you for your attention, and Larry and I will be glad to entertain questions at this time.